Right, now that you've seen the proof of the theorem that the class of regular languages is closed under the union operation, and I showed you an example of the applications of this important theorem, I'm going to show and prove a relative theorem to the first one that we saw, and it relates to the operation of intersection. This theorem, just like the previous one, is about the closure, and it says that the class of regular languages is closed under the intersection operation. In other words, if you have two languages, A sub 1 and A sub 2, and that both of these languages are regular, then the intersection of these two languages is a regular language. The proof idea is basically just like the proof of the union that we did earlier, and the idea is to find a finite automaton that accepts the language or accepts the strings from the language that's the intersection of the two languages A sub 1 and A sub 2. So we start with the supposition that we have a automaton M sub 1 whose language is A sub 1 and an automaton A sub 2 whose language is A sub 2. In other words, automaton A sub 1 accepts all languages from language A sub 1, and automaton M sub 2 accepts all the languages from, or all the strings from language A sub 2. We build an automaton based on M sub 1 and M sub 2 that simulates the operation of these two languages at the same time, and that accepts the strings that both of these automaton accept. Just as the proof for the union, we need to simulate the two automatons side by side and give them at the same time, give them the input symbols, give to both of them at the same time. Proof in this case is also by construction. So again, what we're going to do is we're going to start with our supposition that we have two automaton, we have two languages A sub 1 and A sub 2 that are regular. By definition, there is an automaton M sub 1 that is a 5-tuple Q sub 1 over the alphabet sigma with the delta sub 1 transition Q sub 1 0 start state and F sub 1 accept state that accepts strings from A sub 1, and that there is also an automaton M sub 2, and we write that as Q sub 2 sigma delta sub 2 Q sub 2 0 start state and F sub 2 that accept strings from A sub 2. We will construct a third automaton based on these two automata that simulates the operation of both of these two automatons side by side, and that it accepts the strings that both automaton A sub 1 and A sub 2 M sub 1 and M sub 2 accept, or that will end up with the operations effectively the end or accept states of automaton M sub 1 and M sub 2. So let me just draw these for you, just like the proof for our union operation. We start with the idea that we have these two automaton M sub 1 and M sub 2. And what this means is that we have an automaton M sub 1 with a Q sub 1 0 start state, an automaton M sub 2 with the Q2 sub 0 start state. That these things would perform operations on the input, go through some intermediate states, and they end up with some accept states. And so what we want to do is that if we start with a string, and let's say that this string is a sequence of a sub 1, a sub 2 to, let's say, a sub m, and we want to create an automaton that simulates both of these sequences, both of these state machines, and that if both m sub 1 and m sub 2, when we reach the end of our sequence, if both m sub 1 and m sub 2 are in an accept state, that we will accept, otherwise we will reject. So basically what we want to do is we want to create an automaton m equal q sigma delta q sub 0 and f, such that if the input is a string, let's say w, is given to it, it accepts if both m sub 1 and m sub 2 accept. Now notice here again we have the combination of two automatons. So the way that we will be able to do this is, again, to conceptually, the idea is here to conceptually, when each symbol comes in, to give that symbol to both automaton at the same time. When the next symbol comes in, we give the next symbol to both automaton at the same time, and so on and so forth. The way that we simulate this is through a pair of states, one coming from the first automaton and the other coming from the second automaton. Actually, let me again reiterate this. The way that I'm going to simulate this process of simultaneous operation is that I'm going to, for my constructed automaton here, I'm going to create a state in which the first state belongs to the first automaton and the second state belongs to the second automaton. This way, when a symbol comes in, I will basically calculate or simulate the processing of both of these automatons side by side. So as a result, as such, what I'm going to do here is, and again, this m sub 1, m sub 2 definitions are basically defined such that the automaton m sub 1 accepts strings from a sub 1 and the automaton m sub 2 accepts strings from m sub 2. You can refer to the previous equations and previous proofs that we did. So the first idea is to create our states for the automaton m, which is q. So what I'm going to do is I'm going to make q to be a set of q1i and q2j in such a way that q1i belongs to q sub 1, the states from the first automaton, and q2j belongs to q2, the second automaton. In other words, the q is the cross product of q sub 1 and q sub 2. So each of the states in q is a pair, a binary ordered pair, or a binary pair representation, or binary tuple of states from machine 1 and machine 2. This way, when a new input symbol comes in, I replicate it and I give it to the machine 1, to the machine 2, and then I let them do their process. When another symbol comes in, I replicate it and give it to machine 1 and machine 2 and let them do the processing side by side. So that's part 1 of defining my automaton. Again, the sigma here is equal to both sigmas, because here I have the 3 sigmas the same. Now if sigma 1 and sigma 2 were different, then the sigma is the union of the 2 sigmas, because my final automaton must recognize all the symbols from both alphabets, so I use the union of the 2. In this case, I just simplified it. The alphabet for both automaton are the same, and therefore I use the same alphabet. The third step is the step that that ensures the integrity of my computation. So what I want to do is that when a new input symbol comes in, I want to look at the operation where the automaton m sub 1 takes me, and the operation where automaton m sub 2 takes me. So delta is a transition function that's from q cross of sigma, the alphabet, onto q. It's nothing really important here. It's just I'm replicating or rewriting the definition of the domain and range of my automaton, which is q cross sigma over to q. Now what is q? Q is q sub 1 cross q sub 2 cross sigma over to q sub 1 cross q sub 2. What this means is that each delta takes as input a pair of states from automaton 1 and 2 and an alphabet, and then returns a pair of states from automaton 1 and 2 respectively. How does this compute then? So if delta takes as input a pair of q1i, q2j, remember, a pair of states, one from q sub 1 and one from q sub 2, or one from q sub 1 and then one from q sub 2. Okay, so it takes a pair of states and then an alphabet, a something from the sigma, and then what it does, it generates a pair of states. Now the integrity of my computation is going to be preserved if this pair of states, the first state comes from the first machine and the second state coming from the second machine. So then I'm going to actually go ahead again and reiterate that, show you how this should look like. So the first one should come from the first machine, and then the second one here, actually probably, let me just clear this up. So the first one should come from the first machine here, and then the second one should come from the second machine, right? So what does that mean? That means that the first state is basically where delta sub 1 takes me on q1i and a. And the second state here is the state where delta sub 2 takes me if I were into qj, q2j, and I read a as the input alphabet. Okay, so this ensures that my total automaton, my bigger automaton that's built on the two original automaton, processes each of these states independently over the input alphabet sigma, and then takes me to a new state. So that is the transition function for the construction. For the fourth element, what I would like to see is I would like to have the original state of, or the initial state of my automaton. Basically, since each state is a pair, is a binary, is an ordered pair, basically then I want my machine to start in, so I want both of m sub 1 and m sub 2 to start in their original state, or their start state. So the start state of my overall machine is going to be a pair. The first one is the start state of the first machine, and the second one is the start state of the m sub 2. That takes care of my machine starting in the start state. And finally, the accept state. What would be the set of accept states of my automaton? Again, since the F is a subset of Q, it's going to be a pair. I call this again Q sub I1I and Q sub 2J, such that Q sub 1I belongs to F sub 1 and Q 2J belongs to F sub 2. This ensures that the set of accept state of my my final automaton, my compiled automaton or combined automaton, is a pair of states in which both are accept states, meaning that whatever that string was, when I finished it, both of my automaton M sub 1 and M sub 2 are in their accept states, and therefore both of these machines have accepted the language, and therefore my combined automaton accepts that language. Another way to write this is that since this is Q sub 1 from F sub 1, Q sub 2J from F sub 2, this is equivalent to F sub 1 cross product of F sub 2. Remember the difference. I'm going to actually write this difference right now here so you would remember it. So here, it's important to remember. So I'm going to basically kind of do this. How should I do it? Let me actually put like these, like the 4 dashed line here. So I say in contrast to the union. Okay, so remember the F of union was equal to Q sub 1I and Q sub 2J, such that Q sub 1I belong to F sub 1 or Q sub 2J belong to F sub 2. Remember the difference was this or, and here we've got the and. So the set of states or ordered pair of states of the intersection are the sets in which both states are accept states of the original, whereas the set of accept states for union is a pair of states in which either one of the two or both are accept states. And remember from this one, for the union, we said this is also equivalent to the states to be from Q sub 1 cross F sub 1 or F sub 2 union Q sub union F sub 2, F sub 1 cross Q sub 2. So remember, these two are in terms of the cross product are different. For the union, the cross product is the cross product of the first states, all of them, with the accept states of the second, or the accept states of the first with all of the rest of the states from Q sub 2. Whereas in the intersection, the accept states are effectively cross product of the original accept states. Okay, so now let's take a look back at what we did here and see how we proved this. To prove that A sub 1 and A sub 2, to prove that the intersection of two regular languages were regular, we assume that A sub 1 and A sub 2 are regular. Therefore, there's an M sub 1 that accepts strings from A sub 1 and an M sub 2 that accepts strings from A sub 2. That's by definition. If the language is regular, then some finite automaton accepts it. To prove that their intersection is regular, we built or constructed a finite automaton that accepts the languages, the intersection of the two languages. And once we construct this, then we have such a machine. Therefore, a finite automaton accepts that exists that accepts the intersection, and therefore the intersection is regular. How did we do that? We basically made the state of our construction to be a pair or sets of pairs in which the first state comes from the automaton M sub 1 and the second state comes from the automaton M sub 2. That's the construction of the set of my states. The input alphabet was the same. The transition table or the transition function of my construction takes a pair of states and a symbol and then creates a pair of states in which the first element is created by going through the computation of the machine 1, m sub 1, and the second state in the pair is going through the construction or going through the computation. See, this is going through computation of M2. This is going through computation of M1. Okay, and so that simulates the two machines. I make sure that the start state in both machines are effectively the start state of my union, my intersection, and I make sure that my machine accepts if it ends up in a pair of states in which both are accept states of their respective machines. And by constructing this machine, I just proved my theorem. So next, I'm going to show you an example of how we can use two smaller languages, or rather two simpler languages, to intersect and create a more complex language. Okay, now I want to show you an example of constructing an automaton that is simulating the intersection of two languages. Now this time I'm going to actually do a little bit differently. What I'm going to do is I'm going to build two simpler automaton, and or rather two simpler automata, because automata is the plural of automaton. So I'm going to build two automata for two smaller languages, and then I'm going to build the automaton of their intersection. So the problem that I'm going to show here and to solve is something like this. Let's say that I want to make an automaton, so to create this to recognize this language. Create an automaton, or rather, let's do this. Let's say that we want to prove that A equal to this, W, such that W ends with A and has at least one B, is regular. So prove A is regular. So I want to do this. I have a language A, which is the set of all the strings that end with at least an A and have at least one B. And I want to show that this language is a regular language. How can I do this? It's actually a three-part. First of all, basically it's one part. The part is I need to in order to show that this language is a regular language, I need to show that there's an automaton that accepts the strings from this language, and those are the strings that end with an A and have at least a B. So to do this, notice that I have an AND here. So this is the key part, which means that if I can break this statement into two languages that are simpler, then I can build the automaton for them, therefore showing those are regular, and then use my construction knowledge that I just did to build an automaton that's built off of their intersection, and therefore showing that their intersection is regular. So let's do this operation. Okay, so here's what the language that I want to create. I want to basically make an automaton. I want to create an automaton that recognizes A. Again, A is the set of strings such that W has at least one B and ends with A. Okay, so what I'm going to do is I'm going to look at this language and see that this is kind of complicated to do, but the good news is that it's an AND of two simpler languages. W has at least one B, and W ends with an A. So I'm going to build two languages off of this. So I'm going to say A is the intersection of these two languages, A sub 1 and A sub 2, such that A sub 1 is equal to the set of all W's that W ends with an A, and A sub 2 is the set of all the strings that has at least one B. Okay, so how are we going to build these? These are actually fairly simple machines to build, and I'm going to basically build these. If you don't remember how to do this, revisit the previous unit, Unit 4, in which we showed how to design finite automaton. Basically, the idea is to simulate states. So for A sub 1, I'm going to create M sub 1. Okay, so for A sub 1, I'm going to create an M sub 1 that basically has two states. One state is the state that the string does not end with an A, and the other state is the state that the string ends with an A, and the accept state is the one that ends with an A. So these are going to be my two states, and for simplicity I'm going to call this Q. For simplicity, let's actually call this the first state, call it Q sub not A, so Q sub A bar, and second state is going to be Q sub A. So the Q sub A is the state that ends with an A, and Q sub not A is the state that does not end with an A, and I'm going to show that with a bar on top of the letter. So when I'm starting, so my start state is going to be Q not in A, meaning that the start state either is epsilon, which means that I haven't seen any strings, so that does not end with an A, so that's the start state. Now I'm going to stay in the start state Q not A if I see B's. So as long as I see B's, I'm going to stay here. As soon as I see an A, then I'm going to go to Q ends with A, which is going to be an accept state. And I'm going to stay in that state for as long as I see A's, and as soon as I see a B, I'm going to move back into Q does not end with an A. So I'm going to flip-flop between these two states. So if I end with an A, I accept, and if I don't, then I don't accept. Okay. Now M sub 2 is a similarly simple language to create as well, which means that this language also has two states. One state representing I have not seen a B, and the other state representing I've just seen the first B, which means that now I'm going to accept. So here, then I'm going to call this one Q of 0, meaning that I haven't seen any B, and Q of 1, which means that I have just seen the first B, and from this point on, I'm going to either see another B or not, but this language has at least one B, so I must accept it. So then again, the start state means that I haven't seen anything yet, which means that I haven't seen any B's yet. So I'm in Q sub 0, no B's. And I'm going to stay in Q sub 0 for as long as I see and I keep reading A's. As soon as I read a B, I'm going to go to Q sub 1, which means that now I just saw the first B. And then from this point on, regardless of if I see A or B, I'm going to accept, because the moment I see the first B, I have seen at least one B, which means that now from this point on, any string that is created is going to have at least one B, and therefore that string must be accepted. So these are my two languages that I have, A sub 1 and A sub 2, and accordingly I have the two M sub 1 and M sub 2 being their respective automata. So then let's write these mathematically. So M sub 1 is a set of Q sigma delta sub 1 Q sub not A, and the accept state is going to be Q sub A. Okay. Now we know that delta is A and B, so sigma is A and B, so that's good. So I'm going to go ahead and define its 5 tuples. So its 5 tuples are going to be this. Q sub 1 is going to be Q of not A and Q of A. Its sigma is the alphabet A and B. Its Q sub 0 is Q of not A, and its F is the set Q of A. And now to its delta, delta sub 1 is from the states Q of not A, QA, from letters A and B. So if I'm in Q of not A and I see an A, I go to Q of A, Q sub A. If I'm in Q not A and I see a B, then I stay in Q not A. If I'm in QA and I see an A, I'm going to stay there. And if I'm in QA and I see a B, I go back to Q not A. That's my delta 1. So delta 1 is going to be from Q sub 1 cross sigma over to Q sub 1. So Q sub 1 cross sigma over to Q sub 1. How about M sub 2? Actually, let me just draw a line here as well. So M sub 2 is going to be Q sub 2 sigma delta sub 2 Q 0 Q and the set Q1. Actually, I probably should reformat these. I'm going to call these guys F1, F1 there, and then M sub 2 has a set of accept states called F sub 2. So now let's build these, which is easy as well. Q sub 2 is going to be Q of no B's. Actually, let's call these also QB bar and QB. It makes things easier. So I'm going to be QB bar and QB. That would be my start states. The alphabet is still A, comma B. The Q sub 0 of my M sub 2 is going to be Q of B bar, and the F sub 2 is going to be the set Q sub B. Okay. How about its delta? So delta sub 2 is going to be again from delta sub 1. Delta sub 2 is going to be from Q sub 2 cross product of sigma over into Q sub 2. So I'm going to have Q of B bar. I haven't seen any B's, and I have seen a B, A and B. So I stay in Q B bar. If I see an A, I go to QB. If I see a B, if I'm in QB, I'm going to stay in QB regardless of A or B being the input. And this is my delta sub 2 for the second automaton. So to create the automaton for the overall language, I'm going to create the M to be Q sigma delta Q sub 0 and F. And I already have my recipe for construction. So first, Q. Q is equal to the cross product of the states from the first one and the states from the second one, which basically means that it's going to be a set of four states. So Q naught A and Q naught B, Q naught A, Q B. I'm going to basically cross product these guys with these guys. Q A, Q naught B, and Q A and Q B. It's basically, I've got four states. Each of them is a pair of states. The first one coming from the first element, second one coming from the second. First one coming from the first automaton, and the second one coming from the second automaton. So that's my set of input states. My sigma is going to be equal to sigma, which is A and B. That's not a problem. And delta is going to be from Q sub 1 cross Q sub 2 cross sigma over to a pair of states Q sub 1 and Q sub 2. Cross product. Let me just write it a little bit clearer. So I'm going to do Q sub 1 here. Cross product with Q sub 2. I'm gonna next write exactly what that transition function will be. The set of my, or the original initial state for this is going to be, basically it's going to belong to Q, right? Which is going to be a pair of states. So it's going to be the start states of both Q sub A bar and Q sub B bar. So this pair of the start state of both machines is going to be the start state of my final machine, my combined machine. And then F is going to be the cross product of F sub 1 with F sub 2, which is going to be the cross product of Q sub A, which is this guy, and then set Q sub B, which is this guy, right? So this cross product is going to effectively be the set Q sub A comma Q sub B. That's going to be my final state, which is going to be that set. Okay. One of the things that you need to be careful a little bit about is that Q sub 0 is a pair of states. F is a set of pairs of states. So again, F accept states are set of states. F is a set of accept states, and start state is just one start state. It's just one state. Okay. Now I need to go and define delta. What is delta? Okay. So delta takes a pair, let's say Q1 and Q2, and then an input symbol. Let's call this alpha. And then it generates a pair Q1 prime and Q2 prime, in which Q1 prime is the delta 1 of Q1 and alpha, and Q2 prime is the delta 2 of Q2 and alpha. Just again, I'm going to try to make it clear. See, if I have the delta that takes a pair of states and a symbol, it's going to generate a pair of states. The first state of the pair that's generated is delta sub 1 of q sub 1 and alpha, delta sub 1, okay? And then the second one is going to be delta sub 2 of q, delta sub 2 of q sub 2 and alpha. Okay, this is how you simulate your computation. The delta basically takes a pair of states and a symbol, generates a pair of states. The first in the generated pair is from delta 1 and the first of the input pair. The second of the generated pair is going to be the delta 2 of the second from the input pair. So how are we going to write this now? This is actually fairly easy. I'm going to write my delta just like I did with the delta 1 and delta 2. And here's what is going to happen. What is the input of my delta? My delta input is a pair that comes from q sub 1 cross q sub 2. So q sub 1 cross q sub 2 are these four guys. So let's list them. Q naught A, comma, Q naught B. So that's one. Q so I'm going to do this. Q naught A, Q B. Third one is Q naught A and Q B, Q A and Q naught B. And then the fourth one is Q A and Q B. And my input symbols are A and B. That's easy to do. Now for each of these, I'm going to generate pairs. Okay, so then we're gonna work these. So now let's do. What happens if I am in Q naught A? So actually, let me just do this with numbers. So we'll get to this. So let's see. If I'm in Q A not A and I see an A, what does delta 1 tell me? Delta 1 tell me this is 1, right? So that means that if I'm in Q naught A and I see A, the machine M sub 1 goes to QA, right? So then this is going to be Q sub A, 1. Okay, let's change the color. So let's do this. Let's call this operation 2. What happens if you're in Q naught B, and you see an A? If you're in Q naught B, so this is 2. This is 2. You stay in Q naught B. So this is going to be operation 2. A bad idea. Let's just change the colors to blue. To Q naught B. When it sees an A, it goes to Q naught B. So this is going to be Q naught B. Okay. Now, what's going to happen? Let's call this now 3. What's going to happen if you're in Q naught A and you see a B? So when you're in Q naught A and you see a B, then you're going to stay in Q naught A. So this is going to go to Q naught A. Next, we're going to look at 4 here. What happens if you're in Q naught B and you see a B, right? So what happens if you're in Q naught B, let's call this 4, and you see a B, then we are here. So then we're going to go to Q sub B. Now, what happens if your Q sub Q not A, we see an A, we're going to be Q not A, we see an A, we're going to go to Q sub A. Q sub B, we see an A. Q sub B over A goes to Q sub B. Then again, machine 1 over Q naught A and B. Q naught A and B goes to Q naught A. Machine 2, QB and B. QB and B, we go to QB. Then again, we go to machine 1. What happens if machine 1 is QA and it sees an A? If machine 1 is in QA and it sees an A, it's going to stay in QA, so QA. If machine 2 is in Q naught B, what happens if it sees a B? So if you're in Q naught B, in machine 2, we are here, and we see an A, then we stay in Q naught B. Next, we'll generate QA Q naught B for B. So if we're in QA and we see a B, so if we're in QA and we see a B, we're going to go to Q naught A. And if we're in Q naught B and we see a B, so if we are in Q naught B and we see a B, then we go to QB. Finally, when we are in QA and we see an A, when we are in QA and we see an A, we stay in QA. When we are in QB and we see an A, so when we are in QB and we see an A, we stay in QB. And when you're in QA and we see a B, we go to Q naught A. Machine 1 does. When we are in QB and we see a B, we stay in QB. And this is the machine that performs these operations and accepts the language that is the combination of the two. How does its transition function look like? The transition function of this machine, of course, is a 4-stage machine. So the first state is going to be the pair. First state is going to be the pair of Q naught A and Q naught B, which is going to be the start state. Then we do Q naught A and Q B, Q A and Q naught B, and finally QA, QB, which is also an accept state. So this state is going to be the accept state. I'll do it, double line it like that. Okay. So from Q naught A, Q naught and naught B over A, we go to QA, Q naught B. So when we see an A, we go here. When we see a B, we go to Q naught A and QB. So with a B, we go in here. Then Q naught A and B. With A goes to QA and QB. So with A, we go in here. With B, we go to Q naught A and QB. So with B, we are going to stay where we are. QA, Q naught B, which is this one down here to the left, over A goes to QA and Q naught B. So over A, it's going to stay in itself. With the B, it's going to go to Q naught A and QB. So with a B, it's going to go in here. Finally, QA, QB, which is the one at the bottom here. With both A Actually, with A, it's going to stay here in itself. So with A, it's going to stay in itself. And with B, it's going to go to Q not A, QB. So with B, it's going to go up here. And this completes my machine. And since I could create or construct a finite automaton that accepted the union of the two languages, then the union of these two languages is regular. In fact, from this point forward, if I give you a language and I show that this language is regular, if you can break it down to this intersection or the union of the two languages and show that those two languages are regular by giving automaton for them, then you have proved your machine. But this was an example of, if I give you two machines, M sub 1 and M sub 2, how could you combine the two to build a machine that recognizes both of their languages, the intersection of both of their languages. Now, notice the difference would have been the fact that with the intersection and the union, the difference would be the set of accept states. So if I said, what is the accept states of the union of these two operations, then that would be basically a pair of states where at least one of them is an accept state. So as long as the pair has a QA or a QB, then it would be an accept state. So it's going to be QA, comma QB not, and then QA, comma QB, and QA not, comma QB. This is going to be the accept states for the union will be three states. The states where either QA is an accept state, or both QA and QB are accept states, or just QB is accept state. So that would be a set of accept states of the union. And so you would see basically that the union of these languages, these three states will be their accept state. This one and this one and this one will be the accept states. Okay, now that you've seen a good deal of examples about, one example of how to build an automaton that recognizes the union of two languages, or how to build an automaton that recognizes the intersection of the two languages. And in fact, the only difference was the accept states for the union and the intersection were just different. Let's look at another theorem in regular languages. And that has to do with the closure of the regular languages over the complement operation. In other words, if you have, so basically the theorem states something like this: the class of regular languages is closed under the complement operation. In other words, if A is a regular language, then its complement is also regular. The proof idea is fairly simple. It's basically just like the idea that we used for the proof of closure for intersection and union of regular languages. The idea is we start with an automaton that accepts all strings from the language, and then we build an automaton that accepts all the strings from the complement of my original language. And the process, again, and the proof is by construction. So let's see how it's done. So again, what I would like to show is that if a language A is regular, then its complement is also regular. Proof is by construction. So basically, I suppose that there exists an M such that L of M is A, meaning that there is a finite automaton M, or rather let's call this M sub 1, that accepts all the strings from the language A, I'm going to construct M that recognizes if I could write a complement. So let's start with M. M would be an automaton that would start with a Q sub 1, M sub 1 actually, sigma, the alphabet, and delta Q sub 1, 0, its start state, and F sub 1, a set of its accept states. So the way that it works is that basically Q sub 1 is going to be a set of all Q1 i's to n. Sigma is the alphabet. There's nothing to do with it. Delta sub 1, is going to be from Q sub 1 cross sigma over to Q sub 1, such that the delta sub 1 of Q1 I comma alpha, a letter from the alphabet, will be Q sub 1 J, let's say, whatever, right? So from a state, we see a symbol, we go to another state. Q sub 0 for my state is going to be Q sub 1, 0, start state, and the set of accept state is going to be a set of Q1Js such that Q1J accepts W's from A. So accepts strings from A, which means that if I have a set of strings, let's say S sub 1, S sub 2, S sub 3, all the way to S sub n, when I start here from Q sub 1, 0, then I go through a set of states, let's say R1, R2, R3, all the way to Rn, and then Rn would belong to F, rather F sub 1. Okay? So if you want to look at this language and see how, or this automaton and see how it looks like, it's going to look something like this. It's going to have a start state, let's say Q1, 0, and then it's going to go into a bunch of states, and then it's going to end up in some accept states, right? So if you give it the languages, the symbols S sub 1, S sub 2, S sub 3, if this symbol belongs to A, then at the end of this process, you're going to be in one of these accept states. Okay? So I'm going to now construct a automaton M. I'm going to call this Q sigma delta Q sub 0 and Q sub 0 and F that accepts strings from a complement. How does that work? Now, I would pose you this. Let's make Q to be Q sub 1. Let's make sigma to be sigma. Let's make delta to be equal to the original machine. Let's make Q sub 0 here to be also the start of my machine. So what I'm going to do is I'm going to simulate my original machine, except that I'm going to make F to be the complement of F sub 1. And I pose that this machine actually accepts strings from A sub 1. Why? Because all of the process of these machines, these two machines, are completely identical, except for all the states in M sub 1, which were accept states, now are reject states. And all the states in M sub 1 that were reject states now are accept states, which means that if you draw any string that's not in A, then by the end of that process, you're going to be in, by M1, you're going to be in some state that is not an accept state, which means that it would be an accept state for the M. And to show that this works is that let W be a string that is basically not in A, which means that if you basically break W to S sub 1, S sub 2, all the way to S sub M, and you start with Q sub 0 of M sub 1, and then you process it, then you're going to be in some R M that does not belong to F sub 1, which means that by product of this, then R sub M belongs to F, which means that M accepts W, which means that A complement is regular because we just constructed a automaton M that recognizes all the strings or accepts all the strings that belong to A complement. So again, if W is in A complement, then W is not in A. Then if I break it down to the set of its symbols and I pass it through M sub 1, the last symbol is not going to be in F sub 1, the accept state of my original language, because it's not in A. And since the accept state of my original language is the complement of my final, or my original automaton is the complement of my automaton, that means that R sub M belongs to F, which means that M accepts W, which means that A regular, A complement is regular. Okay, so now that you've seen the closure properties and the proofs of closures of regular languages over the union operation, intersection operation, and the complement operation, let's talk about an example about the complement operation. And usually we use these closure properties in cases that we are asked to build a machine that accepts a certain language, but that certain language is complicated, but its union of two smaller languages or simpler languages may not be complicated, those two simpler languages, or it may be the intersection of two simpler languages, or it may be the complement of a simpler language. So for example, let's say that you're given a language A that's the set of all the strings where W has 0, 1, 0 as, or rather if W doesn't have, if W does not have 0, 1, 0 as substring, okay, or that it does not contain 0, 1, 0 as substring. So thinking of this language, it will be complicated because you need to build a machine that accepts all the other languages, or all the strings that the 0, 1, 0 doesn't appear anywhere in them. Now if you look at this, this is actually equal to the complement of B, where B is equal to all the W's such that W has 0, 1, 0 as substring. And it's much easier to build the language that has, or the automaton that has 0, 1, 0 as substring, or accepts strings that have 0, 1, 0 as substrings, than it is to build the first one. So we're going to build the machine that accepts B. Then according to our proof, if we keep all the processes the same, except that we just use all the non-accept states as accept states and make all the accept state as non-accept state or as reject state. Then we have built the machine that accepts the complement of our language. So to create the machine, let's say M sub B, which is going to be Q sub B, sigma, delta sub B, and Q sub B 0, and F sub B. Then for A, we're going to make M sub A to be Q sub A equal Q sub B. So we're going to use the same Q's, the same sigma, and the same delta. So delta sub A is going to be equal to delta sub B. And then same, so Q A sub 0 is going to be Q B sub 0. Keep the same start states. And then F sub A is going to be complement of F sub B. So if we make this, if we make the machine for the complement language, and if we just flip its accept states with its reject states, then we're going to build the machine that we're asked for. So we're going to first start with the B. How does this work? So the machine that accepts B is going to basically start in a start state. Let's call this Q sub 0. Q sub B0. And this Q sub B0 is when you have not seen the first 0. So as long as you keep seeing ones, you're going to stay there. Now as soon as you see the first 0, right? As soon as you see the first 0, then we go to having seen Q sub 0. And in here, if we see a 0 from this point on, we're going to stay in this Q sub 0, because then we have probably seen 0, 0, or 0, 0, 0, or 0, 0, 0, 0, which means that we are still waiting to see the next one. If we see a 1 here, then we know that we have seen the first two symbols, Q0, 1. Okay, and if as soon as we see, and if we are here and we see a 0, then we know that we have seen all of it, Q0, 0, 1, which means that this is an accept state. Alright, and we're going to stay in here for 0 and 1. Now, if we are in Q0, 1, and then instead of seeing a 0, we see a 1, we're going to reset back. Because now what we have seen is probably something like 0, 0, 1, 1, which means that we're going to just scrap the whole process and go back into start looking for the first 0. So this is a fairly straightforward process for building M sub B. So M sub B was not really too complicated. Now if I wanted to do that for M sub A from scratch with this, it would have been kind of a nightmare. So now, according to my definition for M sub A, all I need to do is to make Q sub A, sigma, delta sub A, and Q sub A0, and F sub A. So this is going to be the same with Q. So I'm going to keep the same process. This is going to be the same for sigma. Delta sub A is going to be delta sub B. I'm going to keep the same transition arrows and everything. The start state is going to be even the same, so it's going to be Q sub B0, and the accept state is going to be complement of the accept states here, which means that now my M sub A basically starts with the same QB sub 0, Q0, Q01, and Q010. Transitions are going to be all the same, so with a 1, I'm going to stay here. With a 0, I'm going to go in here. With a 0, I'm going to stay in it. With a 1, I'm going to go to q sub 1. With a 0, I'm going to go to q sub 1, 0. And then overseeing a 1 from q sub 0, 1, I'm going to go back to the start. And I'm basically now making all the non-start states, non-accept states, to be accept states, and all the accept states, which is here q010, to be a non-accept state. So you see that this language, this machine processes strings, and as soon as it sees a 010, then it flips into a state that it can never recover. And the rest of the process basically stays the same. So so this is basically the idea here. If you have a finite automaton for a language, then to create the automaton for its complement language, all you need to do is to keep everything the same, except that you make all the reject states of the original machine to be the accept states, and make the accept states to be now reject states, just like what I did here. So, so wonderful. We proved the closure of union, intersection, and complement operations over the regular languages. The next regular operation I talked about is the operation of concatenation. And now we want to prove that concatenation is closed under the regular, or the class of regular languages is closed under the concatenation operation. In other words, if I have two languages, a sub 1 and a sub 2, that are regular, the concatenation of a sub 1 and a sub 2 is regular. The proof idea here is that I'm going to build a machine to accept a sub 1 strings, call it m sub 1, and a machine that is called m sub 2 and accepts strings from a sub 2. And now I want to see that if I give it an input string, that half of it, the first half, comes from a sub 1 and the second half comes from a sub 2, then it is going to be closed. So here, what I want to do is that I want to show a string of x, y, where x belongs to a sub 1 and y belongs to a sub 2, and then I want to make this to accept. I want to make the m to accept all these strings. So the idea is to combine these two languages together to make the process work. Now I'm going to attempt very roughly to scale this out and to show it to you to see if you can see why it doesn't make sense to do it just we did with the other two, or rather three operations. So let's say that you have an m sub 1 and you have an m sub 2, and then what you do is that you have a string that can be broken into an x and a y, where you have like x is like x sub 1 to x sub n, and then y is y sub 1 to y sub m. And now we know that m sub 1 accepts this, so m sub 1 accepts this, and then m sub 2 accepts the second part. Okay, and now we want to basically use that same trick that we did with our union operation and intersection and the complement, and see if we can build this machine. There's one slight problem here, that I'm hoping that you can see that we will not be able, with the finite automaton that we have defined so far, to be able to simulate this process. And that is this problem. See, I have m sub 1 to have like a q sub 0 here, and then m sub 2 to have a q sub 0 here prime, right? These are the start states of these machines. And these will go to some states, and then these are going to be some accept states here, and then these are going to be some intermediate states, and then it's going to have a set of its own accept states, M sub 2. So the problem is this, that once I find a way to connect my M sub 1 to M sub 2, which by the way I don't have now yet, and with these kinds of machines I won't, by the time that my machine M sub 1 is processing or rather the symbols from the first part of the string, the machine M sub 2 may be also processing some of these symbols. So there's no way for me to record my symbols, right? And then to have them, to have my M sub 2 to wait for its part in the process. The problem is that all of these symbols are coming one at a time, and once a symbol is fed into this machine, it's going to be gone forever from the process. And so with the current machine, the current toolbox that I have, which are finite automaton, and in fact they are deterministic finite automata, I have no means of constructing the overall M which would accept the concatenations, and this is where I'm hitting a wall. The problem is that if I build and construct my M, then M doesn't know where it has to break the input. You know, should the M break the input from like the middle of this string, or should it wait until the X's are read? But the problem is that I don't know. The M, the overall machine that I create here, M doesn't know when X stops and Y starts. So there's no means for me to put these connections here between the two machines. Should I bring the connections from one of the intermediate states? Should I bring the connections from the accept states? Should I bring the connections from some accept states and some intermediate states? I don't know. M doesn't know. And that's the problem with the deterministic finite automaton, that I cannot build my construction. So at this point, we do need a more powerful toolbox. We need to have another means of constructing finite automata that could sort of kind of guess. And that is the core of what we are going to cover next in the next unit, and it's called non-determinism. We are going to basically next time, in the next unit, show an alternative means of creating a finite state machine that accepts languages that are regular. Then we will show that non-deterministic finite automata and deterministic finite automata are basically the same, and they accept the same classes of languages. Although it's kind of counterintuitive, because once we see non-determinism, you might think that non-determinism is a more powerful machine, but it is, in terms of its power, it's the same as deterministic finite automaton. The difference is that it gives us a lot more flexibility about designing our automata. In fact, the same language, if you go with a non-deterministic automata and a deterministic, the non-deterministic automata will have far fewer number of states in them to accept the same language. So that's their power, but their limitation is that they are limited to the regular languages. And from that point, once we see and cover the concept of non-determinism, then we'll be easily able to prove not only the union, intersection, and complements, much easier than what we did with deterministic automata, but we can also do for star operations and for concatenations. And in fact, what we're going to build is going to be called a class of regular expressions, which is a powerful way of representing strings that belong to the class of regular languages. So I hope that this which is probably one of the highest theoretical classes we will have, covers a good deal of how you would go about working with automaton, at least at this point deterministic finite automaton, how you would basically be able to create machines by union of two machines, intersection of two machines, and complements of two machines. And next we will cover non-determinism. Well, thank you so much for listening to these lectures. The past few lectures have been, I tried to take them very, very slowly, and I hope that you would go over them as much as you need. And these concepts that we covered in the past few lectures are going to be helpful for your next round of assignments, which is going to be due pretty soon.